Welcome to lecture 32. Let's study the stability of finite slopes. This finite means finite height. The height of the slope is finite. It's not infinite like the one we considered earlier. So let us look at a slope of height h. H can be 5 meters, 10, 12, 15, etc. It can't be 100. 200, it's less than maybe about 20-30 meters. And the slope angle is beta, as we said earlier. The properties of the slope are unit weight gamma, cohesion C, and friction angle or angular shear resistance phi. One of the simple methods which was proposed long time back by one Mr. Kalman, we'll discuss this to illustrate the mechanics and the method of calculating. We do not expect failure to be planar, particularly in soils. Planar surface is not possible. Very unlikely, but it illustrates how the method can be used to calculate. So what I would like to take is passing through the toe at an angle. This angle is beta, this angle is theta. So if I say A, B, C, this is D. Let us say this will be a trial failure surface. We do not know where the failure is likely to occur, so let us say it is inclined at an angle theta with respect to the horizontal. So again, coming back to our earlier analysis, I need to know what is the gravitational force, then what is the reaction, normal force, and what is the shear strength that can be mobilized. As usual, we can always resolve this gravity into normal and the shear stress which is causing sliding along AC. So basically we want to calculate W. W, weight of the sliding mass, is equal to gamma into area ABC into 1, which is the thickness of the sliced perpendicular board. How do I calculate this? The triangle ABC, I need to get the area. So height I know is equal to h. I need to find out the length AB. I can find out as AD minus BD. AB length is equal to AD minus BD. And how do I find out? AC is the diagonal and h is the height. So can I find out AD in terms of, if this angle is theta, this is theta, so h by AD gives me tan theta. H is the So h by AD is equal to tan theta, or AD is equal to h cot theta. Whereas BD, this angle is beta. Please remember, this angle is beta. So this angle is beta. So BD will be equal to h cot, this should be cot theta, and this will be cot beta. So this will be equal to h cot theta minus cot. So now we know the distance AB and we know the height h. So the area is equal to W is equal to gamma h into h cot beta cot theta minus cot beta. We know the weight W. So the normal component, like what we did earlier, I can get, which is equal to normal force is W cos theta. Again, please remember the angle between these two is theta. That we are looking at vertical, and this surface which is inclined at an angle theta, and the shear force which is downward T is equal to W sin theta. So I can calculate the normal stress, which will be equal to, normal force is W cos theta is equal to gamma h square into cot theta minus cot beta into cos theta, and the shear force T is equal to W sin theta. So it's gamma h square cot theta minus cot beta into sine theta. And if you want to find out the stresses, I have to divide by this length AC times unit weight, which is unit distance. So we need to find out what is the length AC. AC would be equal to, please note again, this angle is theta, and you want to find out AC, and this is h. So it will be equal to cosecant theta. AC will be equal to h by sine theta, or shall we say h cosecant theta. And so if I want normal stress, sigma is equal to normal force by area, which is equal to AC into 1. So that is gamma h square cot theta minus cot beta into cos theta by h. I'll take the sine theta above. And the shear stress tau, which is acting downward, is T by AC into 1. So it is gamma h square cot theta minus cot beta sine theta by h and another sine theta here. So that makes it slightly simpler. We can write now. So sigma would be equal to cancelling gamma h into cot theta minus cot beta sine theta cos theta, where the shear stress is equal to gamma h cot theta minus cot beta sine square theta. What will be the strength mobilized along AC? Tau mobilized is equal to C plus sigma tan phi. So C plus sigma we write from here gamma h cot theta minus cot beta sine theta cos theta into tan phi. Simply substitute with the tan of the angular shearing resistance, you will get the mobilized. So now you can say what will be the factor of safety for a possible planar failure surface. Factor of safety is equal to C plus gamma h cot theta minus cot beta sine theta cos theta tan phi divided by gamma h cot theta minus cot beta into sine square. Now this is for a given angle, planar surface inclined at theta. We want to find out what is the minimum factor of safety. We need to find what is minimum factor of safety. So when I look at this factor of safety, it is a function of C, gamma, phi, h, and of course theta. What are the terms? Plus of course beta. Function of cohesion, unit weight, height of the slope angle, plus the failure plane theta. We do not know what is that plane which gives me the minimum. So when you go back to your basic calculus, in order to find out minimum, all that you have to do is take the derivative and equate to 0. So if I now differentiate d factor of safety by d theta and equate to 0, you will get the theta critical. What is that critical angle which will give you failure surface? And you will find that theta critical is equal to beta plus phi by 2. That's as simple as that, for particularly the very little friction angle, etc. So you find that as you increase theta, when theta is 0, infinite factor safety because there is no sliding. Theta is equal to 0, no sliding, because the plane is horizontal, so there is no soil which is pushing. When theta is equal to beta, no soil. If I increase theta, equate to beta, there is no soil at all, so no failure. So halfway between these two, you will get the factor of safety. And from here, you can go back and substitute. You will get a very simple expression for the factor of safety. And for factor of safety 1, suppose I say if factor of safety is equal to 1, that means the numerator and denominator are equal, and I can solve for the critical height, which we do. H critical is equal to 4c by gamma into sine beta cos phi prime by 1 minus cos beta minus phi prime. We get a very simple expression for the critical height. What I am saying is, we try to solve this equation for the minimum, and the factor of safety is equal to 1, and in that case we get this expression. And you can see here the critical height, the maximum. If I increase the height more than this, it's going to fail. So I can actually find out the factor of safety is equal to H critical by H actual. This is where you can do that, which means I find out the maximum possible for a given beta, given friction angle, given cohesion, and unit weight. So all the soil properties are given, and you can calculate the critical height, and the factor of safety is the critical height by actual height. And one simple particular case would be if phi is equal to 0. That means purely cohesive soil. Then if phi is 0, cos phi is equal to 1, and this will be, that's equal to H critical is 4c by gamma sine beta by 1 minus cos beta. And beta is equal to pi by 2. What does it mean? When beta is pi by 2, we are looking at this angle beta, slope angle. It's a vertical cut. What happens? H critical is simply equal to 4c by gamma. So this is how we design these deep excavations for multi-storied buildings. If I know the c value, it will be equal to 4 times c by gamma. Let us say c is equal to some 30 kPa. Maximum height of vertical cut, H critical, is 4c by gamma. So when you are making an excavation, for example in Visakhapatnam, Guntur, Vijayawada, etc., where you may get cohesive soils, you can tell the client how much is the maximum height, and he can go without supporting the vertical cut. In Hyderabad, we have no problem because C is very high. Let us say C is equal to some 30 kPa. Gamma usually is of the order of 18 kilonewtons per meter cube. So if I now calculate what will be the H critical when I want to make a deep cut, it will be equal to H critical is 4 into 30 by 18. So this gives me 2, 9, 10, 3. So 20 by 3, about 6.7 meters. With a cohesion of 30 kPa and unit weight of 18, you can have maximum vertical cut of 6.7 meters with a factor of safety of 1. But if you want to have a factor of safety of 1.5, actual H would be equal to 6.7 by factor of safety. That gives me somewhere around 4.3 or 4.56 maybe. So that will be the maximum height you should allow for the construction of the basement. That may be. Whereas in Hyderabad, you can get C of the order of even 100 kPa, which means you have no problem. Most of the time, the cuts can be very deep, provided there is no water. You know, we have derived in the last class that if it's saturated, the strength reduces and the factor of safety becomes very small. So in case of dry condition, safe, but if it is saturated, may become unsafe. That is why you find during rainy season, lot of failures taking place. So this illustrates how we can calculate the factor of safety by postulating a failure surface and finding out the minimum. So the method of slope stability analysis, first you should know the geometry of the slope. Usually it is a planar one, but there may be situations where you may provide a bench or a berm, as we call it. So basically you need to know then we also need to know the height. The second would be the properties, geotechnical, C, phi and gamma. They may be constant or they can be varying. Suppose I have a slope, I may have C1, phi1, gamma 1, C2, phi2, gamma 2, and maybe below here I can have C3, phi3, gamma 3. So you need to find out how the soil properties can vary. The simplest, of course, when all of them are the same. Then we call them as homogeneous slope. C1 is equal to C2 is equal to C3. Phi1 is equal to phi2 is equal to phi3. The next step would be assume a failure surface. And we'll only consider circular arc from now onwards and calculate the factor of safety. Then the next step would be search for minimum factor of safety, which means you have to go back continuously. It's a iterative process. You assume a different failure surface, calculate factor of safety till you get the minimum. This is how we calculate the minimum factor of safety for slopes. Let me illustrate one of the simplest ways you can do, or the simplest problem. Let's look at clay slope with cohesive soil. So we have the height h, this angle is beta. Let me take a typical failure surface passing through the toe, and the center is at O and the radius is R. A, B, C. So ABC is an area enclosed by arc AC and the planes AB and AC. Okay. So what are the things that we need to do? Here again, now we are assuming this soil is moving along the arc. So we call this as rotational failure. Earlier, Kalman's method, where we had a planar surface, we have sliding. Now with an arc of a circle, what we are saying is the mass of soil contained in ABC is going to slide. So how do I find out? First, I find out the centroid. Say this is some point E and the weight W is acting here. Now you find out what is the distance, horizontal distance from the center. That is called x bar. Now you can see W, the weight, into x bar gives me a moment of causing sliding. So moment of forces causing failure is equal to W into x bar, which is counterclockwise, anticlockwise. When this mass is trying to rotate to the right, you will see that the soil below is trying to mobilize resistance. And that resistance is, suppose this is a purely cohesive soil, we said here, in an undrained state, because the failure may be very sudden, can I say it's equal to undrained strength is Cu. And if I now look at a small segment here, the force mobilized is equal to, say I'm looking at small delta theta, arc along, let us say, Mn, subtended by delta theta, arc Mn is equal to R delta theta. And the force mobilized along Mn is equal to Cu into arc length, which is r delta theta. And what will be the moment of this force with respect to the center? Moment due to force along Mn is equal to Cu r delta theta, and what is the lever arm? Is equal to r. The center is here, and this force is along the arc, and if this is the radius, you again agree that the tangent is perpendicular to it. So the force is tangential to the arc, so the lever arm is equal to r itself. What will be the total force? I have to integrate from A to C, and if this angle is, let us say, some theta naught, can I say that arc length is equal to r into theta naught, and all the forces will have the same lever arm. So the total moment, resisting moment, or moment of resisting forces, mr is equal to Cu r square into theta naught. What we have done is basically integrated delta theta from 0 to theta naught. I can say that this came from that same equation, Cr square, Cu r square, 0 to theta naught of delta theta. So when you integrate delta theta, it becomes theta. From limit 0 to theta naught gives me theta naught. So here is the total moment. So when this mass of soil is trying to slide down, what you find is the soil is mobilizing underneath shear strength along the arc length. So Cu into r into arc length is r into theta naught. This is theta naught, r is the arc length. So r into theta naught gives me the arc length AC, into Cu gives us the total force, and each force, if I take the element, has a lever arm of r. So I get this. Now you can say factor of safety is equal to mr by m activating failure. So that is equal to Cu r square theta naught by W into x bar. So this is for a given center and radius r. You may say, why should I take only one point? Can I take another arc? I can take a third one, etc. In this region, I can take a number of points to get the factor of safety. So I search in this space for different centers. So if I have a slope, something like this, and I expect the centers to be in this region, I take different centers and different radii and get factors of safety. Then we do contouring. You know how to do contouring. When you had in surveying different levels, we do how to find out the contours of corresponding to each height. Similarly, we have factor of safety of, let us say this is 2, this is 1.8, 1.6, maybe 1.41. Then you say the least value is 1.41, so the factor of safety for this slope is the minimum, equal to 1.41, whatever is the value. So this is how we do this. The only catch here is how do I calculate W. Rest of it is what you have seen. If I know the weight and the centroid with respect to the center O. We have located the center. You need to know so that I need to know the distance x. In the good old days, when we didn't have computers, etc., people were trying to find out from simple geometry this area and the location. So if I now look at the arc here, let's draw the toe failure. We don't want to make it more complicated. A, B, C, and this is equal to theta naught. Area ABC is equal to area of the sector OAC. First calculate this whole area. minus area of the triangle OAB and area of the triangle OBC. This is O. Then you will get the area of the sector. Once you know the area, multiply by thickness, you get the volume, and multiply by gamma, you get the weight. Again, you know the centroid of the arc, you know the centroid of these triangles and sectors, and you can get the centroid of the sector. So it has to be done either graphically or with some amount of trigonometry. You can easily find out. It's a very tedious process. But when there were no computers and we only had to use either log tables or slide rule, this is how people were doing it. Of late, we have been able to, or they found a simpler version of the same, to do what is called as method of slide, which was given way back in 1920s, and now we have refined the same, given by a Swedish geotechnical engineer called Felinius. We go through exactly the same. This is theta naught. The height of the slope is equal to h. The soil properties are gamma, c, and phi. This is the trial arc. Center is here, and the radius is r. So given the center, we draw a line to the toe. This is called the toe of the slope. What he said was, divide this failure zone into number of slices of equal width. Let us say this width is b, or small b, let us say. And by plotting on a graph paper, I can find out the area of each slice if I know the height hi. These are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The number of slices usually is somewhere between 10 to 15. So what we do is we take a piece of graph paper, we draw the slope to natural scale, draw the trial arc, and this zone of soil which is likely to fail, slide or rotate about the center along this line, which is A, B, C. So it will slide along AC. Okay. So if I divide this, for example, you know this total distance, this is equal to B, and we have 12. So small b will be equal to, B is equal to total width by number of slices. In this case it is 12. So small b is equal to the width of the failure surface by n, which is 12 in this. Then I can measure these distances or the vertical height. So area of each slice is equal to AI is HI into B. So then you can calculate delta WI is equal to gamma into HI into B into, of course, 1, because 1 is perpendicular to the board, the thickness of the. Then we also find out what will be the angle with respect to the center, and I try to measure this angle with respect to the vertical. Theta I angle to the center of the base of the slice, so that I can now take the component of W along the base. Okay, so what is theta I? Suppose this will be fourth slice, this will be theta 4. So let me again draw it a little more clearly. This is the fourth slice, this is the center, vertical. So you draw this line, this gives me theta 4. This is the fourth slice, so I say what will be the angle subtended with respect to the vertical to the center of the base. Okay, so if I now take it, this tangent arc of a circle will be perpendicular, so that if this is B, you can say that the base width is equal to of the slice, suppose I call that as Li, b into secant theta I. This angle is theta I, so this angle also will be theta I. Vertical and the normal, horizontal and the tangent will be exactly the same. So I know the base rate. You also know on each slice the force is vertical. If the number of slices is large enough, I can replace arc of a circle with the tangent, so each of them becomes a plane. So this is B, this is Wi, so this is Wni, this angle is theta I. So you can easily resolve and analyze as before, and all that you have to do, and then since I know Wi, I know Xi, which means what is the distance from O, Xi. I can find out the vertical component and very easily find out the contribution of the moment from these slices. So that is how we can do that, Li. So if I want the total moment of forces causing sliding is equal to sigma I going from 1 to n delta Wi into Xi. As I said, from geometry you can easily find out what is Xi, X1, X2, etc. You know how to calculate the area of each slice, you know how to calculate W, and you can easily find out what will be the moment due to that. And what will be the resistance mobilized? If I just take, for example, phi is equal to 0, I simply will have only cohesion causing or resisting moment. So I can find out the length of this arc. What will be that equal to? B secant theta I. So the cohesive force, the force along the base is equal to Cu into Li, and the moment due to this force, resisting moment, is equal to Cu Li into R. And if I want the total resisting moment, it's equal to sigma I going from 1 to n Cu Li R. So instead of doing all the trigonometry etc., by dividing into number of slices, you are finding out each of the slice, and the geometry being known, I need to only know the height of the midpoint of the slice and the angle the base of the slice makes with the vertical. And from there I can get, and the factor of safety is equal to resisting moment by moment activating moment, which is sigma I going from 1 to n Cu R into Li divided by sigma I going 1 to n W delta Wi into, where did we write that? Into Xi. So this can be easily done with a hand calculation. You need a graph paper with draw everything to scale. Within about half an hour to 1 hour, you can find out. You should try that in one of the cases. You can take H is equal to maybe say 8 meters, gamma is 18 meters, C is about 25 kPa, and you try. And you will do it for a given circle, then we go around, look around for a number of circles and find out what is the minimum value. This is the principle of method of slices.